once again. Today we talk about one of the most important um, uh, discussion of the course, that is polarization. So let us talk about from the basics of polarization. Now when we talk about polarization, it's nothing but the direction of oscillation, right? Now I just take a rope and I try to oscillate like this, okay? I oscillate it vertically, so I can say that my polarization is in vertical direction. Now I just take the same rope and I oscillate it horizontally, so it becomes a polarization in horizontal direction, okay? So that's it, that's how simple is this concept. Okay, now I take one window, so you can see that I am oscillating in vertical direction, and I take one a window which is kind of having a door which is in vertical space, okay, kind of vacant space in vertical direction, and what you will see is that my oscillation is going to pass through this door or this space over here, because this is vertical space over here. But if I give a horizontal oscillation to this door, the same door, this vacant space in the door, so what you will see is that there is no oscillation that is going to pass through. Okay, that is intuitively. You can the figure that you see in front of you are very intuitive. Okay, so I hope that you can actually appreciate the concept of polarization and such kind of devices which are known as filters, okay, or polarizers that you will see in some time, right? So, so now what I am going to do is that now instead of my electrical field polarized in horizontal direction or in vertical direction, I am going to say that it's not going to be vertical or it's going to be horizontal, but I am going to say that it's going to be at a particular angle. Okay, it's not vertical, it's not perpendicular, it's with a particular angle, theta with the vertical direction. Okay, so that's what is this theta. That is my E naught is my electrical field, and it is not vertical or horizontal, but it is making an angle theta with my vertical axis, right? Now what I am going to do is that this is the same thing that the door that I was talking about with the vertical spacing, but instead of that, now I am going to tell that it is a vertical polarizer. That means it only allows the oscillation in vertical direction, right? So now can you just pause the video and just think about what would be the output of this vertical polarizer. Okay, so I think you have paused the video and try to figure it out by yourself what would be the output. Now if you see this, as this E naught is having an angle with the vertical direction, it has its component. It has E naught cos theta, that is a component which is along the y direction, that is vertical direction, and it will have E naught sin theta along the x component, that is the horizontal component. Now as the vertical component is straight, that is vertical, it will only allow the vertical component, okay, because this is a vertical polarizer. So the output will be E naught cos theta, okay, the output would be E naught cos theta, that will be the transmitted wave. Okay, similar to this, if I have unpolarized light, now most of the light that we see is unpolarized light. So that is we see the light from an LED, we see the light from the fluorescence lamp or anything on the ceiling. All of them are unpolarized light source. That is, they don't have a particular direction. I mean, it has it kind of in all the directions, right? Now I use that particular light and I pass through a vertical polarizer again. So you can see this axis, the black lines are nothing but its axis, and that is the vertical. So it is now a vertical polarizer. Now after this, can you again pause the video and see, just imagine or just write it down what it could be. So yeah, so it would be vertically polarized light source. Okay, So you can see that your electrical field, so what all the directions that I am mentioning right now are for the electrical fields. Okay, I assume that the magnetic field would be perpendicular to it, but as of now, just for the simplicity, I assume that these red lines are nothing but the electrical fields. Fine. So this is the electrical field which is polarized in vertical direction. So plane polarized light source, right? Again, plane waves, same as plane waves. Now I am going to pass this electromagnetic plane wave, which is polarized in vertical direction, to another polarizer, and you can see that the polarizer over here is horizontal. So these black lines are horizontal over here. So can you imagine, or you can just think about what would be the output? You can again pause the video and just think about what would be the output. So the output that you will see would be there would be no output, right? The output would be like nothing would be there, because you have the vertically polarized light source and then you pass it through the horizontal polarizer. You will see that there you will get output as 0. Nothing will come out of your second polarizer. Okay. So now what do you see? You see that there are two photos. In one of the photo on the left hand side, you have a window where you cannot see anything, and then on the second image on the right hand side, you can see that it becomes transparent. So so you are trying to just you have some kind of imaging device, and you are just trying to have that camera in front of this window, and what would you put in front of your imaging device, that is your mobile phone, so that you can see through this window, right? In this case, you can see that there is a lot of glare. Actually, this is nothing but the glare which is coming through the external light source. Okay, so the glare which is coming through an external light source, it happens through a particular polarized at a particular polarization. So if you use a polarizer, a particular polarizer, and you try to evade that particular polarization that the glare is going to give with you, and you try to tune it, you will see that at a particular direction of the polarizer, you can actually see no light coming out. There will be no glare actually. So all the light that is going to come out is going to come out from within the house towards the outside. Okay, so that's why you can see what is happening inside the house. Okay, so this is if you use a polarizer in front of your imaging device. Now in the case of tissue, that's the course talks about tissue. So when we now what happens when we interact our polarized light source with the tissue. So now let us try to understand what happens to the polarization of the light once it interacts with the tissue. So there are mainly two types of scattering that occurs. One is weakly scattering, that is kind of semi-transparent, translucent materials like the one that you see over here, like cornea, crystalline lens, vitreous humor and the aqueous humor of the front chamber of the eye. So all of them are weakly scattering tissue material, right? And then there are like strongly scattering, that is opaque or turbid domain, like the skin of our hand, the brain, the blood vessels, the eye sclera, the lymph. So all of them are the tissue components, right? So tissue components are with thick tissue components, and which are like opaque in nature. So once the light interacts with those tissues, it kind of significantly scatters, and it significantly loses its original direction of polarization. That we'll see in some time. How much? Now the question comes that how much is going to lose the polarization? Can we quantify how much is the polarization lost by this interaction of the tissues? Okay, so we'll try to quantify that. How much is the light? How much is the polarization lost? And can we come up with a new term? Okay, so this is a very simple example. You have the light source. This is a light source which interacts with a linear polarizer, and then it interacts with the tissue, and then it again interacts with another linear polarizer, and then the photodetector. Now The LED light source, as I discussed some time back, it is an unpolarized light source. That is, it doesn't have polarization in a particular direction. It will have in all the direction. That's how you can see in this arrows. It has all the direction polarization. Now I am incidenting this polarized light source to my first linear polarization, and you can see this is the axis of my linear polarization. It is on horizontal direction. So can you just pause the video and tell me what would be the polarization after this LP1? LP1 is linear polarizer 1, which is oriented in horizontal direction. So it would be in only horizontal direction. The polarization after this LP1 would be horizontally polarization. It will polarize in only horizontal direction. But after it interacts with the tissue, that is the most important thing. Now after it interacts with the tissue, now assuming that the tissue, as I discussed some time back, this looks like this is actually a breast tissue, and this tissue is kind of a highly scattering domain. So what we do is that we take a very thin slice of tissue, okay, not a big thick slice but a thin slice of tissue, and then we pass a linear polarized light through this very thin slice of tissue, and what will happen? Can you guess what will happen? You can just pause the video and just think about it. So what will happen? It becomes depolarized. Now this depolarized is different than the unpolarized light source. It's very important to know that this is depolarized. That it means that it will have its original direction of polarization, that is horizontal, but now because of the scattering, it will have other components as well. Okay, it would be lower in magnitude as compared to the actual direction, but it will still be there. Okay, but my original direction of polarization is definitely going to be there, significant would be there. And then now I want to quantify this polarization in all the direction, right? So how do I do that? I can use another linear polarizer, okay, and I can just rotate it. Okay, I can just rotate this in different directions. Now once I do it, then I can decompose, or I can just differentiate, or I can just take small components in each direction like this as a function of angle, and then I can just make a graph. Okay, once I make the graph, I can get something like a sinusoidal function, and you will see that these two peaks are there, which will represent this peak and this peak. Okay. Now what will happen? What we have seen is that when we change the tissue from one which is like lightly scattering tissue to another tissue which is kind of densely scattering tissue, like what we see is that there is a significant change in the magnitude of this sine wave. So what we have seen is that you can see there are three lines, three sinusoidal functions over here. So all the three represent something else. So now which are strongly scattering tissues, you will see that the amplitude significantly reduces. And if it is a weakly scattering tissue, then the amplitude is significantly higher as compared to the strongly scattering tissues, right? So now now how do we quantify this? Okay, one way to quantify this is developed by Stokes, and what he said is that we can have components. We can have of this sine wave, we can have four components. One component is at 90 degrees. I will give it as a term as IH. Another component is at 135 degrees. Another component is at 180 degrees, and another component is at 135 degrees. Right. So it is kind of given the terminology as IH, I plus 45, IV, and I minus 45. This is IH is nothing but the horizontal polarization, I 45 is nothing but 45 degrees polarization, I vertical means vertical polarization, and I minus 45 means 135 or minus 45 degree polarization. So it's just a terminology, right? Now what Stokes actually gave was these four parameters I, Q, U, and V. Okay. Now I can define I as IH plus IV, that is my intensity at 90 degrees plus intensity as 180 degrees. Then I introduce one more parameters Q. This is a matrix of 4 by 1 matrix, and I write Q as nothing but IH minus IV, and then U as I of 45 plus 45 minus I of minus 45, and then V as I of circular polarized light source, right circular polarized light source minus intensity of left circular polarized light source. But that is not as of now that we have discussed. As of now, we will discuss it at a later stage. But this is how you actually differentiate. Okay, so now you can write your Stokes parameter in this form as well. So you can write it in terms of IH plus IV. That's already the same thing. This is also the same thing. This one you can just differentiate, or you can just simplify it in terms of this one, and then also IR and IL you can simplify into this equation. Okay, so this is how you can write your Stokes parameters, and you can see that you are going to use extensively the Stokes parameters to call the direction of polarization after the interaction of a particular tissue, or it could be any particular optical medium. We will tell in terms of the Stokes parameter now, instead of the in terms of verbally that it's polarized in this direction or that direction. We'll now tell in terms of Stokes parameters. Okay, now as I was saying, now how much is the, if you want to differentiate, or if we want to quantify how much is the loss in polarization. Okay, how much is the polarization being retained by the electromagnetic wave is given by the term known as degree of polarization. Okay, so that degree of polarization in a generalized term is given as square root of Q square plus U square plus V square divided by I, and degree of linear polarization, that is how much is the light being the linear polarization is being retained after the interaction of tissue, is given by DOLP, degree of linear polarization. It is given by square root of Q square plus U square divided by I, and this is degree of circular polarization, that is how much is the circular polarization retained by this electromagnetic plane wave after the interaction with the tissue, is given by square root of V square divided by I. Okay, and you can see that the degree of polarization would be always between 0 to 1. 1 means that it is fully polarized, and 0 being it's fully depolarized. Okay, so these were the few of the studies that we have performed while I was performing my PhD, and this is a system that was developed. So this is in the bottom, so in the top we have the LED light source, then we have LED holder, then you have a linear polarizing film and a particular direction, and then we have the tissue holder, and again another we have linear polarizer film which we can actually rotate in different directions, a holder to hold that particular film, and this is a photo detector. Okay, so we actually rotate this bottom structure over here to get a different angles, and from there we actually get the degree of linear polarization. And what we have seen is that in the case of normal tissues, the degree of linear polarization is more as compared to the cancerous tissue. Now this is because the in the case of cancerous tissue there is more fibrosis and more disordered arrangement of the cells, and because of which it loses more polarization as compared to the normal tissues. In other words, the normal tissues is able to retain the polarization more as compared to the cancerous tissues. Okay. So now let us see that if the light actually propagates, this is fun trivia, if the light actually propagates, which is kind of a form of pulse. Okay, so you can see that the first one that reaches the camera is the ballistic photons. The one that interacts with very lower instances, it's known as snake photons, and then which interacts significantly with the tissue, like a lot of scattering occurs, that is known as diffused photons. Okay, so can you tell which photons will sustain, or which will be having the original polarization, which will sustain its original polarization after its interaction with the tissue? So you can just pause this video and just think about it, whether it would be ballistic photons, snake photons, or it would be the diffused photons. You just pause the video and just think about it and then just tell. So it would be the ballistic photons, because it interacts, there is no interaction, and it just directly reaches throughout the camera and then it just reaches the camera without any much interaction. Now the one which would be the most depolarized would be the diffused photons. So because there will be a lot of scattering, and because of scattering it will lose its own polarization after it interacts with the photons. So we can have a time gated approach to know how much is the scattering that is occurring. Okay. Now we have learned this thing earlier, that if we have two plane waves which is kind of propagating in with same phase, okay, and there are two plane waves which is propagating in the 150-degree phase shifted, right. So we will see that it is, we will have constructive interference, and this is destructive interference that we discussed in the last class. Now that this is the case when there is a phase shift of 180 degrees. But what if there is a phase shift of not 0 degree or 180 degrees, but there is a phase shift of 90 degrees? What will happen? Now I am passing a two plane waves, but they are phase shifted by not 0 degree, not 180 degrees, but 90 degrees. Okay, so here you can see that this is one of the plane wave at 0 degree, and this is another plane wave, electromagnetic plane, electrical field or electromagnetic plane wave, of course, phase shifted by 90 degrees. So what will happen? So what you will see will happen is that you are trying to superimpose two plane waves phase shifted by 90 degrees, and you will see a circularly polarized light source. This is how you get the circularly polarized light source. So this is where you get the fourth component of your Stokes vector, circularly polarized light source. Now when you see the circularly polarized light source 90 degree phase shifted, superimposed, now there is also the direction. So whether it is circularly polarized or left circularly polarized, right circularly polarized or left circularly polarized, RCP or LCP. Okay, so that depends upon where do you see your wave. So if you, for example, you are standing over here and you are trying to see over here, so you just try to see on how it is rotating. How is the electrical field rotating? Either it is rotating towards clockwise or anti-clockwise. If it is clockwise, then it is known as right circularly polarized. If it is anti-clockwise, then it is known as left circularly polarized, right. So in this case, you can see that it is rotating in anti-clockwise direction, right. You can see this particular arrow which is kind of rotating in anti-clockwise direction, and that's why it is known as left circularly polarized. Okay, so let us summarize the Stokes parameters, and then we'll next class we will talk about Jones vector, another way to quantify the polarized light source. So the Stokes vector is given by IQUV, given by IH plus IV, IH minus IV, I of plus 45 minus I of minus 45, and then V is given by IR minus IL. IR means the intensity in right circular polarized, IL means left circular polarized, right. Another way to write this alternate Stokes parameter definition is this one. So you have IH is nothing but horizontal polarized, so this is already I have discussed. So this is after a, so what you mean by IR is that instead of a single linear polarizer, you actually keep a right circular analyzer. Okay, that's something else that we will discuss in some time, and then you IL means nothing but left circular polarized. That is just to quantify how much is the left circular polarized light source, just the magnitude of it. And this is instead of I, Q, U and V, I can also give it a name as S0, S1, S2 and S3, right. This is S0, S1, S2 and S3, okay. So S0 is nothing but the total irradiation. S1, that is Q, is also can be termed as excess in the intensity of light transmitted by horizontally polarized over the vertical polarized. This is the excess of the light that is goes through in horizontal direction as compared to the vertical direction, okay. And this is the excess, this is again all the excess component in 45 degrees plus 45 degrees as compared to minus 45 degrees. And this is also an excess of light that occurs in horizontal polarized light source as compared as in the right circular polarized light source as compared to the left circular polarized light source, right. So all these things are excess, okay. And in the case of unpolarized light source, the excess would be kind of all 0, so only the first component will be getting. Now for horizontal polarized light source, you will see that your IQUV would be 1 1 0 0. You can just find it out. If it is horizontal polarized like this, so your I and IH and IV, IH would be 1, IV would be 0. So your IH would be 1 minus 0, and this all component would be 0 0. So you get 1 1 0 0. Similarly, for vertical polarized light source, you will have IV equal to 1, okay, and IH equal to 0. So that's why you get 1 minus 1 and then 0 0. Similarly, for plus 45, you have 1 0 1 1. For minus 45 degrees, like this one, you have 1 0 minus 1 0. Right circular polarized light source, you have 1 0 0 1, and left circular polarized light source is 1 0 0 minus 1. So this is how you can write the Stokes parameters for each of the light source which is polarized in a certain direction, okay. So which directions we have just mentioned only are 6 directions as of now, okay. So if it is any other than direction, you can write it in the form of theta, okay. So I hope this helps you to understand the Stokes parameters. This is the basic way how to quantify a polarized light source. In the next class, we will talk about Jones vectors, Mueller matrix, and how we can use those terminologies to differentiate between different kind of polarizations. Okay, thank you.